All right, I told y'all I didn't care about whether or not you explained so much on this problem, but I was looking for two different things. Some of you missed the mark on that and you only gave me one thing. I wanted to see the transformations on our standard basis vectors as well as that standard matrix. So finding the standard matrix, we chatted about a lot in class, so most students were completely fine finding the standard matrix as just all of those coefficients from our map. So our standard matrix was 2, -6, 4, 5, 0, -2, and -1, -2, -4. Right? This is because as we chatted about, the other way to write out what S is matrix multiplication or a matrix sort of equation almost, right? Where we have this S of our input here. The pre-image is our A matrix, we'll call this thing A, times that vector and domain, right? That's the other way we could have defined this. We could also have found the standard matrix using those transformations on the standard basis vector, which was that piece that a lot of folks left off. So that transformation, that's when we say, okay, what would happen if I transformed, I don't like the look of that, it's still too long, our standard basis vectors, right? We could write it that way. This is recognizing, again, that idea that, okay, well, if I had some x, y, z, I can see how many x's I need in each of these, and x is just the first element of this. So if there wasn't a y and a z, if I plugged in just one, if I did this operation with just a 1 and then a 0 and a 0, I'd end up with just 2, 5, and -1 as my result, right? As my image of that standard basis vector. And you go, oh, that I, right? And so, okay, cool. I've got this 2, 5, -1, cute. And that's it. You could actually show it to yourself by evaluating and figuring out what those images are, or you can just recognize after we've done this a handful of times that we can go, okay, well, we can even use that shorthand that was introduced to us to say, okay, I just have the coefficients for that particular component. So we have 0, 6, 0, and -2, and S of E3, well, that is 4, -2, -4. Now, one other issue we had, I wrote it down, it happened so many times, was a lot of students here wrote, not a lot, two of you, but it was important enough that I think it's worth saying, wrote this additional piece here, right? We had our transformations, the standard basis vectors, we had the standard matrix. I think students were really saw this word by computing, and they wanted to show how these two things were related. And so a lot of students wrote, okay, S of E1, not a lot. Again, I think it was just 2. But enough for me to, and strong enough students for that I feel like we should talk about. They wrote this. Now, mathematically, what you just said is if I add these vectors, and we know vector addition, that I get out a 3x3 matrix. This is not how vector addition works. We've spent so long in vector addition land that this should feel like there's absolutely no chance that anyone would ever write that. And like I said, 2 stronger students wrote this. And I was like, what in the what? We don't really have a nice way to write it. If we want to, we could, instead of writing that the sum of these vectors is equal to A, we could do something more like this, where we write the matrix brackets, right? And then we write each of those column vectors, and this is just sort of implying that we're writing these columns next to each other. This is fine notation. This is okay if you really wanted something to show that you were computing and not having to write something out, but adding them, that was definitely an issue because that would result in a 3x1 vector and not a 3x3 matrix. So if you want to be I'm appending them to each other, that's a totally different thing you need to be able to write.